Construction spending in China is growing at close to 10% a year, and China is now the second largest emitter of CO2 after the US. According to the Environmental Protection Agency, on some days, 25% of the pollution in the Los Angeles air comes from China's coal-fired power plants and factories, from China's cars, and from the dust created by droughts and deforestation in Asia. China's per capita income is on track to be equivalent to America's by about 2030. And if the Chinese aspire to own cars at the American level, which is 3 for every 4 people, then it will see over 1 billion new vehicles by that time, more than doubling the world's current fleet. They will require more oil than the entire world actually consumes now. And to accelerate the pace of change, here comes the new Nano, developed by Tata Motors in India. It sells for $2,500, and it's been nicknamed the people's car. These changes are coming. There's no question. Technologically, the easiest solution is to transition from oil to another fossil fuel. For example, the world has plenty of coal, enough to satisfy our energy needs for a couple of centuries. In 2007, China was building an average of 2 new coal-fired power plants every week. But coal is even more carbon intensive than oil, so this is not a low-carbon solution without some kind of CO2 capture and storage. And this requires more energy. In fact, it's a fairly common theme that pollution control measures which protect the quality of our air and our water consume more energy than operating without such measures. Capturing, compressing, and injecting CO2 into deep geological formations, or the ocean, increases the energy needs of a power plant by up to 40%, and the cost of the energy produced accordingly. But it can be done. The CO2 produced at the Great Plains Synfuels plant in Beulah, North Dakota, is being transported by pipeline over 200 miles to Weyburn, Saskatchewan. There, it's injected into an old oil field, producing this incremental oil that helps to pay for the project and permanently sequesters the CO2. Unfortunately, the oil produced subsequently creates more CO2 than was buried. And since appropriate sites for sequestration are few and far between relative to the many locations where it is generated, transportation costs are a significant barrier. Nevertheless, researchers are working on ways to bring the cost of carbon sequestration down. Another fossil fuel resource that is being considered is oil shale. This is rock containing kerogen, which is a precursor of oil. The Green River Basin in Colorado is estimated to contain 1 billion barrels of oil equivalents per square mile, and there are over 1,000 square miles of it. It's one of the largest fossil fuel deposits in the world, possibly larger than all the oil reserves of the Middle East. And it's in our backyard, so the temptation is great. Now, strip mining the rock like coal and then extracting the oil is really not economically feasible. But starting in 1996, Shell developed a method called in situ conversion for extracting the oil. Basically, the company drills these shafts and drops electric heaters down them, which heat the ground to about 350 degrees Celsius for 2 to 3 years. During this time, the kerogen is converted to volatile hydrocarbons that boil off and are captured. Shafts around the perimeter have to be filled with a refrigerant that is frozen to create an ice barrier around the site to prevent the oil from contaminating the groundwater. Shell claims that this extraction is economic at $30 a barrel, but it is hugely energy intensive. To extract even 100,000 barrels a day would require the world's largest power plant to generate the required electricity. There is, as you can imagine, intense opposition in Colorado, motivated by concerns about pollution of local water supplies and the impacts on fish and wildlife. A non-fossil option, which is discussed quite a bit these days, is nuclear power, which is inherently low carbon. And there has been a bit of a rehabilitation of the nuclear industry in some European countries, notably Finland, for this reason. But some countries never abandoned nuclear power. For example, France made a strategic decision during the first oil crisis in the 1970s to build nuclear reactors. And today it generates 80% of its electricity in this way, as well as selling surplus electricity to its neighbors. Its reactors used enriched uranium-235, And the enrichment technology, while probably safe in the hands of the French, is something that we are justifiably apprehensive about making widely available around the world. The French deal with their nuclear waste in part by reprocessing or recycling it. This takes care of about 85% of it, although the technology for extracting the fissile uranium and plutonium is also a proliferation risk. Yet for all the French years of experience in this industry, the 15% of the waste that is not recyclable is no better handled than it is in this country. There are now 220,000 tons of depleted uranium and some reprocessed uranium stockpiled in France. A deep geological repository has been investigated, but not yet implemented, in part due to intense public opposition. Some of us would argue, and I think my colleague Professor Cohn would agree with me, that the risk here is just too great.